Welcome back. So, where were we? Yes, relational databases and spreadsheets. I want to say a few more things on that. In some professional communities, the spreadsheet is actually a programming environment. Like there are people who use Visual Basic and all these programming languages. It's incredible what you can do with it. But there was an update recently of Excel. I assume at some point maybe LibreOffice or FreeOffice will do the same. There was a recent update in which they started introducing data frame capability, like formulas that actually emulate the relational algebra and all kinds of things you can do on tables and data frames. And it's extremely powerful. And if you have the theory that you will get in this course and in Big Data for Engineers, you will be power users of spreadsheets, because then you can use all these capabilities knowing the theory behind it and understanding what you are doing. So this is becoming like the link between the two is becoming very tight. Okay, so now a bit about data models, because I already told you what data is, what information is, what an information system is, what structured data means, unstructured, semi-structured, fully structured. So now models are basically used in many fields, also in physics, and it's basically an abstraction of reality. The real world is very complex. If you have to capture, for example, what's going on in this room, if you want to do it perfectly well, you would need to know the position and velocity of every single molecule that there is in this room. That doesn't make sense, right? Or we don't have the capabilities to do that. So what we've been doing for thousands of years is that we just abstract away. We have some, for example, this is a chair, you can sit on it, this is a table, all of these are abstractions. And then when you go, for example, that's the Schrödinger equation that you see here, that is also an abstraction of reality. That's basically a reversible evolution of a quantum system. Maps are also an abstraction. There's people whose full-time job it is to basically make maps, map Switzerland, map the world, the streets, what is where, finding the, this is called GIS, Geographic Information System. There's also full programs at ETH that cover this. Models also at scale are representations of reality, but in a different size. Economic models, for example, all of these fancy curves. And in fact, the data model is something very similar to that. It looks like this, actually, when if you work in a company and the business analysts who prepare a database that you're about to implement, it looks like this. So don't be scared. I mean, I can very quickly tell you what this is about, but after you take the lecture, it will be easy. These are basically the names of tables here. This is a table, 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 and these are the columns of the table. So this is this kind of a description. And the little rows that you see here are basically ties between the tables. You tie the table to each other. That's called the join, basically. And we'll look at this in this lecture. But basically, this is the sort of diagrams that you can see in a company that the business analysts might do. This is a rather small one, actually. So you have much larger and scarier diagrams than that. I saw some of them at ETH. Like really, you could cover the entire room with these diagrams, looking at all the systems, right? So the database design theory, when I told you the advanced part, is about how to design that well, how to pick the columns, the tables that you need for your system. But this is basically a model, right? This is a data model. Now, what's the relationship between shapes and models? Because I told you there's these 5 fundamental shapes, and then there's the models. Well, the relationship is that for every shape, you might have multiple models. For the table, you have the relational model. So this one, there, at first, it seems to be only one, but we'll see there's flavors of it. You actually have several variations of the relational model, but these are all tables. Then you have models for data cubes. You have also several models for trees. There are XML models, JSON models, and even there are several XML models. So you see, for graphs, there's a model called the labeled property graph, which is a mathematical model for graphs. For text, LLMs, large language model, it's also called that way, right? With actually vectors. It's a high dimensional vector space that you have when you store the text. So again, I repeat, for each shape, you might have multiple models, but every model corresponds to one shape. right? It's very rare that you have a model spanning multiple shapes, right? Some people try that. I mean, there's unifying attempts to unify several shapes. But the easiest way to think about it is there's 5 shapes and every shape might have multiple models. A model is basically a description of what the data in that shape looks like. Next week, we are going to study the relational model. We'll spend an entire 2 hours on that. It will be mathematical. So if you don't have enough math today, then you will have math next week, a lot of math. Basically, just to give you a flavor of that, or if some of you want to review a bit, you need a bit of set theory. You need to know what a set is, what a function is, you know, that kind of things, like elementary logic theory or set theory. But I still remind you of what all of that is, right? Okay, so these are models. Now, these two, so tables and cubes, we'll cover in that course. The ones with trees and graphs, it's called NoSQL. NoSQL was also a hype at some point. It means not only SQL, even though some people think it means no SQL at all, but it's a matter of interpretation. And then text, that would be LLMs or information retrieval, ChatGPT, and so on. All right, now a bit more about information systems. They're absolutely everywhere in the world. And in fact, with the internet, we have even more of them, like social media, like LinkedIn. This is an information system. A newspaper has an information system. Now, when you read the papers online, flight booking, train booking, these are all information systems. The maps, when you navigate with your smartphone, a store where you buy something that also has an information system, like when you buy from Digitech or Migros or a chain of supermarket, they also have information systems for the inventory of the shops and so on, right? So the banks have an information system when you withdraw money at an ATM and so on. There's all an information system behind that. And once you've taken this course, then you will understand how it actually works behind that. Many of these systems are SQL-based relational systems. Some of them are not, because they hit the limits of what SQL can do, and so they use something more advanced. But really, most of the systems are SQL. Sometimes I get emails like from students or people working on projects looking for advice. They had in mind of using some modern things like, I don't know, MongoDB or NoSQL and so on. But in fact, in most of the cases, what they really need is a relational database management system, PostgreSQL or SQL. It does the job perfectly well. Simple to learn, it's quite standardized, it's free. You can even use them for free. So there's a lot of advantages, right? But there is something that's going on, is that there's more and more and more and more data and more and more and more and more lookups. So you might think that's a huge transformation, but in fact, in many projects, there's not so much data. The data fits on a single computer and you don't necessarily need to go towards big data. And even if you do, you can still use SQL and the relational model. Even if you have petabytes of data, in some cases, you can still do that, right? So even though it's accelerating, it's really amazing that many people thought in the 2000s that all of that would be thrown away. You know, all the good old relational databases, that's the past. Absolutely not. And SQL is making a comeback right now. All of the big companies, Google, Amazon, and so on, SQL is back. It's all on the marketing documents, like you can use SQL with our system and so on. So this is becoming a hype again. Now, regarding this, what's going on with big data, I can also very quickly tell you a few words about that. We call that the 3 V's of big data, so volume, variety, velocity. Volume has to do with the quantity of data. I recommend you learn these prefixes. You probably know the first ones from the size of disks or, you know, megabytes, terabytes, and so on. It's a good idea to learn the others. Rona and Quetta are actually quite recent. Iota is enough for the size of the entire visible universe, but somehow it still wasn't enough. And I think it's with the mass of Jupiter that they still needed Rona and Quetta as with the number of zeros to have a few more zeros. Okay, so it's a good idea. This is standardized. It's for the whole world. This is an international standard, these prefixes. You can use them with any units, with the meter, with the gram, with the bytes, and so on. Okay, there's also the powers of 2. So this is for geeks. I'm a geek. I love powers of 2. And people actually also came up with prefixes, because you might have noticed that 2 to the power of 10 is very close to 10 to the power of 3, right? 1,000 versus 1,024. So this is why some computer scientists like to use powers of 2 instead, right? But don't worry too much about this. That's really not something that I'm just telling you as a curiosity. This is the one you need to learn. All right. Quick trick. Tera is close to tetra, which in Greek means 4. Peta is like penta, 5, hexa. And that's how you remember the groups of zeros. Tetra has 4 groups of 3 zeros. Penta, 5, has 5 groups of 3 zeros. Hexa, like hexa, has 6 groups and so on, right? So there's a bit of this Eselsbrücke to remember this. Okay, Rona is like nonna. I mean, it's already done on purpose that they did that. Okay. Now, what does it look like to the user? Well, this is probably what you see as a user. You connect to a website. Guess what? There's probably a SQL database behind it that actually has the data. This here is only the surface. It's a representation on your screen with a website, but behind this, there is a database system, SQL or not. So now you might imagine you start from scratch and you would like to implement a website like this, your own web shop in order to sell whatever you want to sell, right? So you might think, okay, let me just take some hard drive where I store the data, and then I can just write a few lines of code, probably in Python, because it's quite popular at the moment, or maybe R or whatever language you want. And you just start and write your program in Python that will produce the web page and so on and store the data on the disk. You can try that. It's going to be a lot of work, very complicated, and probably with many bugs to fix at the end. So this is the naive approach, but actually you shouldn't. The correct way to do it is to use a database, a relational database management system that comes off the shelf that you can just download for free and use. So I would like to give you the intuition of why that is, why you should not do this. You should not try to write it all from scratch, but you should use a database management system. So here's why. Imagine that now a company would do this. They don't want to download an existing system. They want to build theirs, but they're a company, so the data, they have the payroll of the employees, the orders of the customers, the products, the stock, and so on. And imagine they want to write everything themselves with different databases all over the place and themselves. What's the sort of problems they are going to have? One problem they are going to have is the redundancy. The problem they are going to have is maybe on the computer that stores the payroll of the employees, there's going to be redundant data with the orders, maybe because the employees also order some things from the company, maybe with special discounts. So there's going to be redundancy. Why is that a problem? Because if the address of an employee changes, you need to change it maybe on the left, but you also need not to forget to change it on the right. If you forget to change it, you're going to have inconsistencies. Right? So this is the first sort of problem that you're going to get if you try to do it yourself, directly programming your own system. Right? This is the first issue that you are going to encounter. The second issue that you are going to encounter if you try to do things like this is that often you need to combine the data from multiple sources. For example, here that would be the products and the payrolls. Why, for example, if there are salespeople who sell certain products, and you want to use the data from both sides, it's actually very hard to combine. This is not theory, this is reality. You can go to companies, talk to people. Many companies do have, in fact, systems like this. They might be using databases, but different databases. And many of these companies try to combine the databases together. It's a huge headache, and they have a lot of issues doing that. They even came up with a name for that. It's called the data silo. It's because all the databases are isolated from each other, and it's very difficult to combine, right? So there's companies that even have thousands of databases. Even ETH has many different databases, right? So it's really not easy. But anyway, here I even said, imagine they don't even use database management systems, but just program it themselves. Like they write a computer program that communicates with the user and that saves data on this from scratch. Well, here's the top 5 of why they should not be doing that. And instead, they should use something like PostgreSQL or a real database management system. The first reason, or 5 if I count down, is what's called an integrity constraint. For example, if you're a bank, you might want to make sure that the accounts add up, right? That what there is on your account corresponds to the sum of the transactions. You might also want to make sure that there's a positive balance, you know, that sort of things. This is called an integrity constraint. If you do it yourself, you have to implement it yourself in Python. If you use a database management system like PostgreSQL, you get it off the shelf. It's a feature of the program, right? You just specify the constraint and it's going to make sure it holds for you, right? So this is one, it's automatically done. The second thing is that if you write a program and you're the only user, that might work. But if your company grows and you have 10,000 people who access the database or 1 million customers on your website, things are going to break. But if you use a database management system, it can handle the users. It's part of it, right? So you also don't have to worry about that. You create users, you create roles, and then you can even decide who accesses what. Another feature is data loss. If you implement it yourself, you need to worry about backing up the data, about making it redundant in case you lose it, and so on. But if you have a database management system, it has features to actually automatically back up, and even in the modern systems to replicate the data, so that if there is a fire or an earthquake, then you don't lose the data. That also comes from a database management system. Another one is access control. If you are a company, you probably don't want everybody to see the data. If you are a bank, for example, you don't want anybody to view the customer data, right? You might want only the advisor or customer to see the data. So this is called access control. And again, with a database management system, you also get that as a feature. You can specify who can access what in your system. And finally, you're going to save a lot of money. Because it's free. A lot of them are open source and free. So you also have some that you need to pay for. So IBM, Microsoft, and Oracle would be the big three. But the main reason for the cost is the support, that you basically get a team that supports in case of problems. But this is really important because if I asked you to write one from scratch, you take Python and you write it from scratch, it's going to cost you millions of dollars, literally millions of dollars to achieve that. Why would you spend millions of dollars if you can just download it and use it, right? So this is really because this is the sort of things that people need to do just once, and then they share it with everybody else, and then you basically have it all done, all of these features. Okay? So in this class, we'll be using PostgreSQL, but there's a few others. There's MySQL, there's many other systems. Right? They're very close to each other. If you learn PostgreSQL, you will see that any other is going to be easy to learn. Okay, so now one more thing. This system that you are going to use that gives you all that typically is structured in layers. So basically, you're going to have a persistency layer that takes care of storing the data somewhere. And typically, it comes with some business logic on top. The business logic is basically PHP or Java or whatever code that basically interacts between the website and the database. And then the user interface, that's basically the website, that's HTML. Do we have a question on Zoom?
So there's a question. What's the difference between SQL and the SQLite?
Oh, SQL is a language. SQLite is a product. Right. So SQLite is basically, as far as I understand it, I didn't use it a lot. It's a very simple implementation that allows you to use SQL to directly access data on the disk like CSV file. I think that's my understanding, right? You will be able to use it if you visit this course, yes? Yeah. Serverless, yes, you can do it in this way. I'm going to repeat what you said just because you don't have microphone. You basically said that it's serverless and that the engine is very lightweight and directly accesses the disk compared to PostgreSQL, for example. Yeah. By the way, serverless is also a very hype word at the moment, also in big data. The idea that you bypass the servers and provide functions as a service. Yeah. So thank you for the precision. All right. Okay. So we have typically these layers. And we have these layers everywhere. And now comes the magic, what we call a database. That's yet another piece of terminology. What we call a database is, in fact, the data itself. Many people say database for the system, but the database is the data itself. A database is an organized collection of data, right? So this is the entire database. And when you start using that kind of product, it feels like this. And it's stored on disks, but you still consider the whole thing a database. And this layer, that's called the database management system. Right? So the database is the data. The database management system is the software. PostgreSQL, SQLite, or whatever system you use. Many people just say DBMS. DBMS is database management system. So if you see DBMS, then don't be surprised. That just means database management system. So that's the actual software that you can usually get for free, and that is going to take care of managing the data instead of you. The two of them together is called the database system, right? I repeat, the database is the data, the database management system is the software, the two together are the database system, okay? All right, now getting back to Edgar Code. You remember Edgar Code? That's the person who basically was at the origin of the revolution of databases. Well, the brilliant idea that Edgar Code had is that you should make a very clear separation between what's going on down there with the disks and the logical layer, the user. What Edgar Code said is we need to separate the two very cleanly. We call that a physical layer and a logical layer. And that means that for the user, when you interact with a database management system, one that deals with tables, then the user sees tables and relationships between the tables, right? This is what they see. What they do not see, because that's completely hidden, is the files and the indices. This is hidden, right? So if you have a data-independent system, you should have a clear separation between the two, and the user only see tables and relationships. In the past decades, things have been going a little bit backwards, because now you see, especially on social media, some influencers that teach you how to use Python and to directly read the data and so on. This is a bit going backwards compared to this, but now there is again a movement forwards that gets away from this again and encourages the use of data independence. So you see, it's a little bit like a yo-yo in terms of trends. But basically, you need to understand that if you do this separation, then the user doesn't need to know a lot of computer science. It only needs to learn what a table is and how to use SQL, and all the rest just happens automatically. That's the benefit of data independence. Edgar Code 1970. So another way of looking at it is that you have your logical model, the table in here, that you use with SQL, and physically that could be stored in files and directories, or on a clay tablet that works also very well, it's just a bit slower, or you can store it in a data center, or on DNA, people actually did that. They implemented the storage of a relational table in DNA and executing SQL on top of the DNA with chemistry. It's very impressive, but this also works. But you see, there's one thing that didn't change here. That's the table up there. That's data independence. You can change the physical implementation, but you don't change the logical layer. This is why learning SQL and the relational model is so useful, because it keeps being used even with data centers, even with an evolution of the physical storage. And you don't need to know biology to use it, because again, you would still be using SQL and tables. So that's something you are shielded from. So if you zoom a little bit, technically the physical layer, that's basically the piece of software you download, that PostgreSQL, SQLite, and so on. It changes rather rarely. You might get updates, you bring it up to date and so on. But this is basically what takes care of the layout of the files on disk. In this lecture, we don't really care about that. That just happens automatically on the drive. Then you have some conceptual layers. So these are the tables and so on. So here we have data independence between the two. So this is basically SQL and the tables. And in fact, people also, so here we have the structures of the tables and so on. So the schemas, we'll dive into that. And some people like to add yet another layer. You could kind of also call it data independence, but in another way. The layer is basically the fancy web page that you see, because the people who connect to Digitech or Copatome or whatever, they don't see SQL or tables. They see a fancy web page with the pictures of the products and so on. So that can also be seen as some sort of separation between two layers, right? So it's a different kind of data independence. Okay? And that might change often. You might see that if you connect every month, it changes a little bit, that's just as the website gets evolves over time, right? But this is something that happens all the time. So this is also called a view over the data or a mask over the data. Okay, so you can also view these as files on the physical layer, tables on the intermediate layer, and applications on the top layer, the website. Okay, another thing that's good to know on the very high level is what kind of jobs there are in databases. Well, we have people that are the administrators or the sysadmins. They are going to give access to people, they will monitor the system, they will make sure that it's running and so on. So the big companies have people full-time doing that, right? So they make sure that, everything is functioning normally. Then you have database designers. They are the ones who draw the fancy data models I showed you, right? So with the tables, the names, the columns, and so on. So database designers, they structure the content of the data. There's a whole business in consulting, like consulting companies who do this, like migration of databases and so on. So there's a whole market for these things. Then you have the programmers. These are the people who write SQL and Java and PHP and JavaScript, like all of these. These are programmers. Then we have people that query and update the database, but they don't do it like as a backend of a website. They more do it like directly against the database. They write a SQL update, a SQL query, and directly query the database. This is in fact what we'll do in this lecture. We'll tend to do it like this. You sit in front of your notebook, you type SQL, and you see the results. Then there are people who don't like to actually see any SQL or even any computer code. That's not a problem because there's software that even hide this, and that's typically in many companies, like for example in call centers or in customer for the customer advisors, the client advisors. They have software that gives them a view over the data, but they don't have to write any SQL. It just appears nicely. They type some text, it searches it, then you see the customer view and so on. So these are let's say the customer-facing people. Okay, so just to tell you that there's a whole ecosystem of people working on these databases. Then what does it look like? So now you know the database is the data itself. DBMS means database management system, right? So that's the software. The database itself typically can be stored on the local drives, can also be put on a server on a network drive or even shared like this. So you see there's many ways to make that happen, or even on a distributed file system in a cluster, right? You can have 1,000 machines that store together the database. Now I'm going to scare you a little bit with these scary words, but basically there's part of the database that manages the data manager, and that's called data manipulation language. You can see it as the part of SQL that manipulates the structure of the tables. You add a column, you change the name of the column, and so on. No, sorry, that's the other one. That's called data definition. When you change the name of a column, you change the name of a table, you change the structure of the table, that's data definition, right? You look at the metadata. When you modify the contents of a table, you modify a value, the address of a customer, the name of the customer, that doesn't change the structure of the table. You're just changing a value in the middle of that. That's called data manipulation language, right? And that also can be done with SQL. So you can manage the data or manage the metadata, right? And when you put everything together, you have the metadata and data manager. That's part of PostgreSQL. It's part of the DBMS. And DDL, data definition language, and DML, data manipulation language, that's basically SQL. That's what we learned there. That's the interpreter, right? Transactions, I'll say a few words about that. It's easy to understand. A transaction is the thing that makes sure that if you go to the ATM and you get the banknotes in your hands, that it's also going to be taken from your accounts, right? That's what the transactions are about. Or in a flight booking system, that two people are not going to be on the same seat. Right, so this is what the transaction manager takes care of. All right. I'm throwing a lot of terminology at you, right? Data, information, structured data, data shape, data model, data definition language, data manipulation language, and so on. Database management system, database system, right? So that's a lot, but it will equip you with all the high-level terminology for the semester. Now, DDL, data definition language, it's about the structure of the table. There's a name for that, it's called a schema. The schema is what the tables are going to look like. What there is in a schema, and we'll look at it probably in 2 weeks from now, we'll look in SQL how it looks like, that tells you the structure of the tables, what columns do we have, what types the column have. There's, for example, a date in the birth date column. There's a string in the name of a person column. There's an integer in the age column. So these are the types. And there's integrity constraints. So these are all the constraints you want on your table. The balance has to be at least 0. That must be the sum of this and that, and so on. So this is all you specify in a schema in the metadata. This is what it looks like. That's an example. So I say I have 3 columns: customer ID, security ID, quantity. And in yellow, you have the types. Customer ID is an integer, security ID is a string, quantity is a positive integer, and so on and so on and so on. Right? You might have an integrity constraint that says strictly greater than 0. If it's 0, you remove it. Right? And these are the types in yellow. I'll try to be using yellow. I think I'm using yellow on the other side. So the types will be in yellow. And on top of the types, you have the names of the columns. So that's a schema, right? That's a schema, and that's what a data definition language does. In 2 weeks, I'll show you how you can do that in SQL. In SQL, you can say what columns you want, what types you want. So that's the schema. That's the table that comes after that schema. So you see customer ID is an integer, security ID is a string, quantity is a strictly positive integer. So that's the actual table. Okay. Now, what's really nice is that when you have a schema, then the data might be valid or not valid, right? So on the left, this is valid. Why? Because customer ID is an integer, security ID is a string, and quantity is a positive integer. But look at what's on the right. This is not valid. See, that's not an integer. That's broken. That here is also not a positive integer. It's a negative. So this is broken. The benefit of using PostgreSQL or a database management system is that this is never going to happen. It will not let you. If you try to do it, you will get an error, right? So you have the guarantee this is not going to happen. And at all times, you're going to have a nice table that respects the schema, right? So that's very nice. And basically, the people who draw the diagrams, they decide on what this has to look like over here. And then what happens is that once you have the schema in the constraints, data has a life, right? Why? Because people connect to your website, they change their address, they place an order, the inventory changes. So the content of the table is going to change. In fact, it changes every second, right? If you're a web shop, it keeps changing. What doesn't change though is the schema. The columns, the types, the constraints, this stays the same. It's just the content of the table that evolves over time under the constraints that it must be valid against the schema. For whom is that clear? All right. Now, a few words on the languages. Now it's the manipulation side. It's sometimes blurry between DDL and DML, but we'll go in details in the next few weeks about that. Who knows languages? Programming languages, at least one. I suspect most of you probably heard of those on the left, right? Python, very popular at the moment, Java, C, C++, R, and so on. These are called imperative languages. But there's other languages that are called declarative. The difference is actually relatively simple. It's the difference between cooking at home or going to the Mensa. If you cook at home and you use a recipe, then the recipe is going to tell you what ingredients to use, and it's going to tell you in what order you're supposed to do what, right? So you put the sugar, the eggs, and so on, you stir, you preheat the oven, and so on. This is imperative. Going to the Mensa means you go there and you ask for the veggie menu, right? That's declarative. You say what you would like. Of course, they still cook in the background, right? It still happens, but you don't do it. Other people do it. It's the same thing with declarative languages. You see SQL in there, that's where it is. There's others. Who heard of Haskell, Camel, and so on? Not so many of you, maybe computer scientists more. So these are functional declarative languages. The declarative languages basically mean that you just tell the machine what you need. You declare what you need. The rest is taken care of. The machine is going to figure it out for you, right? So that's the difference between the two sides. SQL is a declarative language. That's what makes it a bit easier to learn than Python or Java, as we will see. You declare what data you need. Now, if you look at what these languages do in the entire ecosystem, so that's the same thing I told you about already with the physical layer and the logical layer. What happens is that the user itself, so that will be you in this lecture, they use SQL. They declare in SQL what they would like to see. But inside, on the physical layer, PostgreSQL is a piece of software, right? So it has to have been programmed by people. And in fact, it's usually programmed in an imperative language. So PostgreSQL itself is likely to have been implemented in something like C++ or Java or whatever language. But this you don't get to see because you just directly download the software and that's it. So this is all hidden from you. But typically you do use an imperative language for the implementation of the database management system, right? Then on the physical layer, you might have heard of assembly code when you're at the level of the CPU, so the processor of the machine. But this is one layer below, okay? So the really nice aspect of declarative languages and imperative languages again has to do with data independence. It again has to do with that because on the physical level, you typically will have an imperative language. And on the logical level, you're going to have a declarative language, right? And the imperative language is going to be hidden from you, right? And what's actually going to happen, there's a lot of things you don't see, but that actually happen, is that when you enter a query in SQL, the database management system, so the piece of software, PostgreSQL, SQLite, is going to come up with a master plan. They're going to try to figure out how they are going to give you what you want, what you declared in SQL. So this is called the query plan. It involves a lot of optimization and figuring out the fastest way to execute it, possibly with indices. It might even involve parallelism. If you have a data center with 1,000 machines, then physically you might be using these machines. As the user, you will see nothing of that. You just see that it's going to be fast, but you don't see the actual action, right? So this is the nice aspect of a declarative language, is that it's completely disconnected from what's happening below there, right? So this is just still SQL that you use. Is it out of batteries or is it on strike? Maybe the battery, oh, maybe it's the last slide. Could that be that it's the last slide? Oh, yes, it is actually the last slide. This is why. Okay. Do you have any questions? No questions. Right. So today I was careful. I could have thrown already math at you and scared you with all the mathematical formulas of the relational model. But for that first week, I think you already probably had a lot of being busy with getting started in the semester. So I kept it high level. Next week, we are going to work on the relational model. That's going to be a bit theoretical. What I recommend, if you want to prepare yourself a little bit and make sure you know what a set is, what the element of a set is, a function and so on. But don't worry, I will anyway rehearse this with you and make sure that everybody is on the same page, right? Just want to make sure, because you're from different departments, so you might not have the same backgrounds, but I really want to make sure that everybody can follow, right? So we'll do the math. But don't worry, with the math, I will also give you the intuition, because the nice thing is that even though it's math, we can always visualize it very nicely with the tables, just like the clay tablets, which were thousands of years ago. Okay, who wants an early lunch in the Mensa? Okay, shall we go for lunch? Okay, so thank you very much, everybody. I'll see you next week. No exercises today, so I'll see you next week at 10 for the relational model. Thank you very much.